All right, this set of notes we've been talking about phase changes, solid, liquids, gases. We've also talked about boiling and freezing points. Today, though, I want to focus on really what sort of things can have an effect on boiling and freezing points. Before we do that, just a quick review. If you have a solid, liquid, and a gas, at this point you should know what each of these is called. If I go from a solid to a liquid, of course, you know that's melting. You know that liquid to a gas is vaporization. You know if I skip the liquid phase, we would call that sublimation. And it turns out that each of those is what we would call endothermic. Endothermic. Endothermic meaning you have to add heat to them. Now, what if we go the other direction? If I go this way, gas to a liquid over here, gas to a liquid would be condensation. Liquid to a solid would be freezing. And you can skip this stage, and that's called deposition. So that should be a little review for you. The other thing I want to do is just talk about phase diagrams real quick before we get into the notes specifically that we're talking about. Phase diagram is just what happens when you go through all the phases. So what we would do is you'd add energy down here, and you would have temperature in degrees Celsius over here. And let's just make this for pure water. Okay, you can make a phase diagram for anything. So let's start out below the freezing point of water, maybe -10. And let's say you know water freezes at 0. Freezes at 0. And you also know it boils at 100. So a phase diagram would look like this. The temperature would rise if you started adding energy. It would be just in the solid form only. Okay, 0, you know the temperature will level out during the phase change. When the entire phase change is over, the temperature will rise again. And then at 100, it would boil, and it would level out again until you had basically, at some point, all of the liquid would be gone, and it would all be in the gas form, and that gas can also increase in temperature. A couple key points to talk about on here. This point right here would be called the melting point. This point right here would be called the boiling point. If you go back the other direction on the graph, in other words, if you took energy away from a gas, at the point that it started to condense and turn back to a liquid, you'd call that the condensation point. It would start condensing until you had basically all liquid. Then you would get the temperature to drop again. And at this point right here, it would freeze. So we would call that the freezing point, going back the other direction. Now, if you take a look at each line on here, so if you look at each line, what phase would each line represent? Well, this line right here would represent having basically now on your notes you might want to write it out completely. I'm not going to do that. Switch colors though for you. You would have basically a solid only if you could look at this line right here, if you were looking at it. Then here, as it starts to melt, you would have both liquid and solid present. So on that line, you would have liquid and solid. Both of them would be there. And then once you start rising in temperature again, once you get to here and it starts to go up again, you would have basically melted all of it. You'd have only liquid left at that point. So this would be liquid only. And you get to this point right here, you would start to see gas bubbles forming in there, so you'd have both liquid and gas present. So on the straight line, liquid and gas. And then on this dotted line, I drew it dotted because it's not something we've taken the temperature of in the class, but you would have gas only at that point. All right, let's talk about what impurities do to boiling points and freezing points. Well, let's first talk about boiling points. Well, sorry, telephone call. All right, boiling points. If you add impurities such as salt to water, so I have a beaker here, some water, put a thermometer in there. You guys all know that water normally boils at about 100 degrees Celsius. Turns out if I add impurities, salts, or other things to it, I actually increase the boiling point. So adding impurities increases boiling points. This isn't the exact reason why, but it's a good way to remember why. The way I would think of it is water has to turn to a gas and then escape. And if you add salt, the particles could run, I'm sorry, if you add salt, the water vapor might start to run into the salt and make it harder for it to escape. Again, it's not the exact reason why, but it's a good way to remember it. It's like adding blocks to getting it out, okay, or roadblocks for the water vapor to escape. So you'd have to increase the boiling point. So maybe now it boils at 110 instead of 100. And that would work for other liquids too. So, for example, we might add ethylene glycol to water and put it in our radiator. That way it doesn't boil as fast, etc. Okay. Freezing points. What about freezing points? Turns out impurities drop the freezing point. So let's say I had some water, and it would normally freeze at 0 degrees, of course, right? So you've seen people add salt to the road before. So if I add some salt to, it might be it's already frozen, so let's say instead of 0 it was like at -5 degrees outside, so the water already froze. If you add salt to it, what happens is it drops the freezing point, makes it even harder to freeze. So now instead of freezing at 0, it might not freeze until maybe -10 degrees out. And if it's only -6 out, well, it's going to melt on us. Okay. So impurities drop the freezing points. All right, what about pressure? Pressure actually has the tendency to increase boiling points. And again, I'll kind of give you an analogy to help you visualize it. Water, for example, normally boils again at 100, and that means it would be turning to a gas, right? And then trying to escape as a vapor. Well, the way I like to think about it is if you were pushing down extra hard on the surface of the water, you increase the pressure, it's going to make it harder for that water vapor to escape. And if I make it harder to escape, I'm going to have to heat it even more. So now instead of boiling at 100, it might boil at 120 degrees Celsius if I increase the pressure over the water. This is exactly how a pressure cooker works. It basically puts a lid over a container with just a little tiny opening, so as water starts to vaporize, turn into a gas, it starts to build up pressure in the container. And if it builds up pressure in the container, it raises the boiling point, and it makes it the temperature of the water increase. So if I put my potatoes in my pressure cooker, they're going to end up cooking faster. And of course, it would have the opposite effect. If I lower pressure, it will decrease boiling points. So, just a little analogy here. If you live at the ocean, we would call that 1 atmosphere of pressure from the air. And if you climbed a mountain, we'll just say it's Mount Everest because you're an amazing climber, and you tried to cook your food at the top of Mount Everest, and you try to cook your food down at sea level, we'll just say the water's already boiling and you put some pasta in there. Here's my pasta. So you have some boiling water. Well, it turns out at Mount Everest there's not as much atmosphere, so there's less pressure. I don't think it's quite a half an atmosphere, or more than a half, but we'll just call it half of an atmosphere of pressure just for the sake of discussion. So you lessen the pressure over the food, or over the boiling water. So now at Mount Everest, your water might be boiling at like 65 degrees Celsius, whereas down here at sea level, it's boiling at 100 degrees Celsius. And you'll cook your food much faster here, and it will take way, way longer to cook your food up at top of Mount Everest or near Mount Everest. I'm not for sure on that. If there's any mountain climbers in your family, you can ask, but I think they use pressure cooker type things to do that, to increase the pressure over their food. Well, let's end up our discussion with pressure affecting freezing points. And at this point, we actually really have to separate water from other substances because increasing the pressure on water affects its freezing point one way, and increasing the pressure on just about anything else does exactly the opposite. So let's just start with water, and I'll tell you what happens, and then I'll try to explain why. So basically, at the bottom right of my screen, if you increase the pressure, you lower the freezing point of water. So why is this? Well, water is, of course, like we've talked about before, it's kind of strange. So what I did is I have two boxes here. And let's say this represents the liquid form of water. What happens to water when you freeze it? What happens to its size? And of course, you know, as a solid, it expands. And this is pretty much the only substance I know of that does this. It actually gets larger as a solid. So let's say you know it freezes normally at 0 degrees Celsius. So let's just say it's, make it a little colder. Let's say it's -1 degree Celsius. So that would cause it to freeze, and we'd have an ice cube. Well, what would happen if we increase the pressure around that ice cube? So we started squeezing around this ice cube in all directions. If we could push really, 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 really hard, harder than you could squeeze physically, the atoms in here, the molecules in here, which are kind of far apart right now as a solid because it expanded, would start to look more like it did when it was a liquid, with them a little closer together. So if I squeeze really hard, it will force the molecules or the molecules to look like it did when it was a liquid, and it will actually make it become a liquid again, even perhaps at -1 degree Celsius, so you can force it back to a liquid. So if you're, whatever pressure that was that caused it to do that, you'd have to actually increase the pressure more to finally freeze it again. I'm sorry, you'd have to drop the temperature. Sorry, you have to drop the temperature even more to freeze it again underneath that pressure. So in short, you increase the pressure, you drop the freezing point. Now for everything else, it's pretty much opposite, and here's why. Let's draw two boxes again. And I'll switch the color because it won't be water. Let's say it's gold or something. So draw this box, and let's say it's a liquid, and then I freeze it, make it cold, turn it into a solid. Turns out as a solid it's actually even smaller. So it's exactly the opposite as water. So the particles in the liquid are further apart from each other, and the particles in the solid are closer together. This is what most things are like. So now imagine increasing the pressure. If I started increasing the pressure around the liquid in all directions, I'm going to force it to look like that. And so this will actually, if you increase the pressure, you will increase the freezing point. In other words, you'll make it freeze at a higher temperature than normal. So that's pressure's effect on freezing points.